Hello, everybody. This is Dave Ockley. I am welcoming you on behalf of the Gauge Theory Virtual. A couple of announcements to get us going as I'm admitting people. First is just some comments about use in the meeting. I think I may starting everybody out muted. If you have a question, raise your hand, and then I'll interrupt and ask Jinfeng your question. If I don't see your hand raised and answer, you can unmute and ask it yourself. Have some patience with me. I'm sort of still on a learning curve for Zoom. Another announcement is in the chat. I've put the link to the Gauge Theory Virtual website, and with that link, we'll have a series of talks. The next talk will actually be on Wednesday, April 8th. It will be John Baldwin. We will keep the website posted with the current things. At the end, we will leave things open to have questions and discussions and questions. I think now I will turn it over to Jinfeng Lin, and I'll mute myself to let the seminar begin.
Shall I start?
Yes, please.
Okay, yeah, I guess my connection may be unstable. Okay, but we will see. Okay, thanks everyone. Yeah, thanks the organizer for inviting me give this talk. And I think it's my great pleasure to speak at this Gauge Theory virtual seminar. I think this is a fantastic idea of this virtual seminar, and I'm hoping to see more of this kind of seminar in the future. And today I'm going to talk about a project using gauge theory and homotopy theory to study four-dimensional topology. And my title is Isotopy of the Dehn twist on K3 connected on K3 after a single stabilization. Okay. So as a start, let me give some background review. And I noticed that there are a lot of experts in the audience in four-dimensional topology, and I have to confess that I'm far from being an expert. So please feel free to interrupt me if I say something silly or make any comment you want. Okay, all right, so understanding smooth structures on four manifold is one of the most difficult topics in low-dimensional topology, and a major reason for this difficulty is that dimension 4 is the first dimension where the smooth category is significantly different from the topological category. Namely, a lot of results that hold in the topological category will actually fail in the smooth category. So let me give a few instances. And the first instance is combine the groundbreaking work of Simon Donaldson and Mike Friedman. And by their work, we know there exist simply connected four manifolds that are homeomorphic to each other, but not diffeomorphic to each other. So this is the first instance of such exotic phenomenon for simply connected four manifolds. And nowadays, looking for exotic smooth structures on simply connected four manifold has been a huge area in four-dimensional topology. So it's impossible to list all those significant results here. Okay, so that's the first instance. And the second instance was a result by Danny Ruberman in the back to the 1990s. Danny found a pair of diffeomorphisms, F0, F1, from some simply connected four manifold X to itself, such that they are topologically isotopic to each other, but not smoothly isotopic to each other. Again, so this shows that in this diffeomorphism isotopy problem, smooth category is quite different from the topological category. And further examples are given by Oakley, Kim, Melvin, Ruberman, and Akbut, Baraglia, Kono, and Krohammer-Morovka, and many, many other people. Forgive me if I did not list all the names. And the third instance of such phenomenon can be obtained by combining a bunch of big results by Wall, Perrin, Quinn, and Donaldson. And it states that there exist embedded spheres S1, S2 with simply connected complement, such that these embedded spheres are topologically isotopic to each other, but not smoothly isotopic to each other. And okay, so these results implies the existence of such spheres, and explicit construction were given by Oakley, Kim, Melvin, Ruberman, and Akbut. So we see that from these three instances, we see that exotic phenomenon appears in a lot of problems. In particular, in these three problems, which we call as the diffeomorphism existence problem, problem number 1, and the problem number 2, we call it as diffeomorphism isotopy problem. And problem number 3, we call it as surface isotopy problem. So I guess it's a good place to ask if there is any questions. No? Okay, good. Okay, now let's move on to the next slide. And then I want to talk about stabilizations on four manifolds. Classically, stabilization means doing connected sum with some standard pieces. And in our situation, we are interested in stabilization with respect to this S2 cross S2. So you can imagine it as a four-dimensional analog of the torus. Okay. So namely, a stabilization means taking connected sum of X with S2 cross S2. There is also a closely related notion of the so-called twisted stabilization. That means taking connected sum with a twisted bundle S2 twisted cross S2. Or you can say it's just a connected sum with a CP2 and CP2 bar. And I want to note that when for a simply connected four manifold, if it is non-spin, then doing this twisted stabilization is just the same as doing stabilization. And today we'll mostly focus on the first stabilization, the untwisted one. And I want to make the remark that stabilization, this operation actually annihilates a lot of gauge theoretic invariants. In particular, it makes the Donaldson polynomial invariant and the Selbert-Witter invariant vanishing. So this is a challenge for using gauge theory to study this operation, because doing this operation will just make those invariants zero, and you can't use them to say interesting things. But I want to make a further remark that there are some other gauge theoretic invariants that may survive under this operation, namely Fintu-Shell-Stern's tooth torsion invariant and the pin-2 equivariant Bauer-Furuta invariant. It's an interesting fact that they are both defined for spin four manifolds, and they both use the spin manifold. The spin structure on the four manifold in some interesting way, and it turns out these two invariants may survive under the untwisted stabilization. Okay, any questions? No? Okay, so let's move on to the next slide. And a basic principle discovered by C.T.C. Wall in the 1960s states that, okay, so we know exotic phenomenon appears in a lot of problems in four-dimensional topology. But Wall shows that, well, such phenomena will eventually all disappear after sufficiently many times of stabilizations. More precisely, now we know the following result. First, Wall shows that for any pairs of simply connected homotopic equivalent four manifolds, they become diffeomorphic to each other after sufficiently many times of stabilizations. And later, Gaunt and Craig, they remove this simply connected condition and they prove a generalization of this result for any orientable manifolds. And actually, they also prove a result for non-orientable manifolds, and that involves a single twisted stabilization. And by the example of Capel-Shanderson, Craig, and Arkwright, we know that in this non-orientable situation, actually one twisted stabilization is needed. And then the next result we know about this principle is by the combined work of Craig and Quinn, and that says for any two homotopic diffeomorphisms F1, F2, self-diffeomorphisms on some simply connected four manifold XX, after sufficiently times of stabilization, they become smoothly isotopy to each other. So here, stabilization, we have to be a little careful by saying this because, in order to connect his sum with the identity map on these n copies of S2 plus S2, both F1 and F2 must fix some small balls in X. But that can always be done and by doing some smooth isotopy. And this is a well-defined notion of stabilization. And the result of Craig and Quinn implies that for any homotopic diffeomorphisms, F1, F2, they become smoothly isotopic to each other after sufficiently many times of stabilization. And the next result is by combined work of Wall, Perrin, and Quinn, and which states that for any homogeneous surface, two homogeneous surfaces with the same genus and simply connected complement, they become smoothly isotopic after you do external stabilization. Namely, you do connected sum with a lot of copies of S2 plus S2 away from these two surfaces. So all these four results actually reflect the general principle that sufficiently many times of stabilization will annihilate this exotic phenomenon in all these three problems, namely the diffeomorphism existence problem, the diffeomorphism isotopy problem, and the surface isotopy problem. Okay, then I hope the discussion I made make this question natural, namely, how many stabilizations do we actually need in each of these three problems? And there has been a lot of significant progresses in understanding this question. And let me give a few of them. The first one was made by Baker Snoking, and this states that exotic pairs of simply connected non-spin four manifold produced by standard method, namely the log transformation, knot surgeries, and the rational blowdowns. Such exotic pairs, they all become diffeomorphic after a single stabilization. So a single stabilization will be enough to annihilate exotic phenomenon in this case. And the next family example was given by Oakley, Kim, Melvin, Ruberman, and Arkwright. And in their examples, exactly one stabilization is needed to make the self-diffeomorphisms and embedded surfaces to be smoothly isotopic. And another remarkable progress towards this question is the following theorem by Oakley, Kim, Melvin, Ruberman, and Schwartz. So this theorem states that for any homogeneous surfaces F1 and F2 with the same genus and simply connected complements, they become smoothly isotopic to each other after a single stabilization. So we just need a single stabilization to make them smoothly isotopic to each other. And well, we need to assume that these two surfaces are not characteristic. Namely, the homology class is not the Poincare due to the second Stiefel-Whitney class. Okay, they also prove a similar result for characteristic classes, and that use a single twisted stabilization. So as you can see from these three instances I list here, it sounds like one stabilization is always enough, right? And this motivates the following speculation. Maybe one stabilization, a single stabilization is always enough in all these three problems. And so that concludes the first part of my talk. And is there any questions?
Actually, can I ask a question?
Sure.
Could you remind us of what's the definition of homogeneous spaces?
Oh, well, they are the same. They are in the same homology class.
Oh, okay.
Okay, so let's move on to the next part. Okay, so let me give the statement of the main theorem. Let's keep this speculation in mind, and we will talk about the main theorem. Okay, so before giving the statement, let me then twist on K3 connected on K3. Okay, so recall that K3 surface is given, well, if we just care about the smooth structure, then it's given by this specific quintic equation. It's an algebraic surface in CP3, and it's the most important example of spin 4 manifolds. And we let X be the connected sum of two copies of K3. Then this is a spin 4 manifold with the following intersection form. And in particular, we know the signature is negative 32 and second Betti number equals 44. Okay. And since X comes from a connected sum, we know there is a neck of the connected sums, namely it's a product of the 0, 1 interval with the 3 sphere. And because there is this neck, there is an interesting self-diffeomorphism on this neck. It's defined, we call it delta 0. It's defined by sending Tx to T alpha Tx. So alpha here, alpha is the essential path in SO4. So a two-dimensional picture is like this. Okay, so this is a two-dimensional Dehn twist. It's a self-diffeomorphism from this neck to itself. That equals identity near the boundaries. And we can extend this then self-diffeomorphism to identity and get a Dehn twist on this connected sum K3, connected sum K3 to itself. So this is the Dehn twist started by Peter and Tom in their recent paper. Okay, so let me. Yeah.
Selman has a question.
Okay.
Selman, if you want to just ask your question, you can unmute.
I think there's some minor mistakes. There are three hyperbolics, right? Not 6.
Sorry. Well, we have 2 copies.
Oh, 3.
There are 2 copies, so
okay.
6.
Okay.
Yeah.
I draw my objection.
Okay. Okay. And so then let me give the statement of Peter and Tom's recent result. And the result states that this Dehn twist is not smoothly isotopic to the identity map. Okay. And okay, this result was proved by studying the non-equivariant Bauer-Furuta invariant for families. And this Bauer-Furuta invariant was first defined by Bauer and Furuta, and in the setting of single 4 manifold, and then later it was generalized to family setting by Xu and Sudvik. And also by a theorem of Quinn, notice that delta induced identity map on homology. So it is topologically isotopy to the identity. So therefore, delta is indeed an exotic element in this mapping class group of diffeomorphism mapping class group on X. So it's a natural question to see what happens if you do stabilization on this delta. So by Queen's and Craig's theorem, we know that if you do sufficiently many times of stabilization, delta will be eventually smoothly isotopy to the identity map. And now we're ready to give a statement of the main theorem. It states that if we do one stabilization on this Dehn twist, namely we connected sum this Dehn twist with the identity map on S2 cross S2, this self-diffeomorphism is still not smoothly isotopy to the identity map. So that's the main theorem I want to talk today. And it's this theorem provides, as far as I know, it provides the first example of exotic phenomenon on simply connected four manifold that do not disappear after a single stabilization. Well, as I said, I'm not an expert in this area, so please feel free to correct me if that's not true. I would be curious to know if there are any earlier instances of such thing in the simply connected case. Okay, and implication of this theorem is that one stabilization is generally not enough in this diffeomorphism isotopy problem. And it's actually form an interesting comparison with this result that one stabilization is enough in the surface isotopy problem. And this theorem is proved by studying this pin2 equivariant Bauer-Furuta invariant for families. So recall that Peter and Tom proved their theorem using a non-equivariant Bauer-Furuta invariant. And by studying its pin2 equivariant version, one can get a slightly stronger result. And let me say, this idea of using this family version of Gates theoretic invariant to study smooth isotopy problem was first given by Danny Ruberman in the 90s, and this idea of using this equivariant Bauer-Furuta invariant appeared in a lot of earlier works, in particular Baraglia, Cornell, and Krohammer-Morovka's work.
I think Selman might have another question.
Okay.
Yes, just curious. Smooth structure by that diffeomorphism, do you get an exotic copy of that manifold? Stabilized.
Sorry, you mean exotic?
Yeah, you pull back the smooth structure of X connected sum of S2 cross S2 by your diffeomorphism to source. Do you get another copy of that manifold? Smooth copy?
Oh, okay, I see. I don't know. That's a good question. I don't know. It looks like it may, but I don't have any proof of that. It seems like these two smooth structures have all the Gates theoretic invariant of these two smooth structures are the same. So I don't really know. I don't know how to distinguish them, but I also don't know how to construct a diffeomorphism between them. Yeah, that's a great question.
Wait, I mean, if there's a diffeomorphism though, then they're diffeomorphic. I mean.
Oh yeah. Okay. Yeah. There is a diffeomorphism. Sorry. Yeah, they are the same smooth structure. Yeah.
I see. They are the same manifolds.
Yeah, they are the same manifold. Yeah, they are the same. Sorry.
Okay.
Yeah, they are the same manifold. They are the same manifold. Yes. Okay, let's move on. Okay, and let me give some idea of the proof. Okay, so as the standard way to study this isotopy problem, one can form a mapping torus of this Dehn twist. Okay, we denote this mapping torus by M, so it's a 5-dimensional manifold. And we also do mapping torus on the one stabilized manifold. Okay, so, and these are both 5 manifolds, but you can also treat them as spin four manifold bundles over circle. So they are just circle family of spin four manifolds. And we want to show that this NST, this stabilized mapping torus, is a non-trivial bundle. Because if we can show that, that will imply that the holonomy delta ST, this holonomy is not smoothly isotopy to the identity. And in order to show this, it's enough to show that the Bauer-Furuta invariant of this family is non-zero for both spin structures. So we know X has a unique spin structure. The fiber has a unique spin structure. But if you form the family over S1, there are actually two different spin structures for these families. And if we can show that the Bauer-Furuta invariant for both spin structures are non-vanishing, then it will imply that this bundle is non-trivial, because it's not hard to see that for the trivial bundle with the spin structure pulled back from the fiber, the Bauer-Furuta invariant is always vanishing. So the trivial bundle will have at least one vanishing, will have at least one spin structure with vanishing Bauer-Furuta invariant. And here, let me recall that this pin 2 is just a one-dimensional Lie group sitting inside.
Can I ask you a question?
Sure.
Is it not true that S-cobordism theorem hold for dimension 5? So this has to be a trivial bundle, since the pi1 of X connected sum these cross S1 is Z as a smooth manifold.
No, I don't. Okay, so you're saying this. I don't think the cobordism theorem is true in this dimension, right? Yeah. I think it's true in higher dimension, but I don't think it's true in this dimension. I mean, well,
Okay.
you can, well, okay, so here, oh, sorry. I guess if you treat it as a phi manifold instead of a four manifold bundle, as a phi manifold, as a five manifold, yeah, I think that's true.
Sorry, what is the cobordism that we're looking at to apply the edge cobordism theorem?
So, like you can still think of a cobordism from S1 cross this manifold to the trivial S1. I mean, it's saying that it has to be a non-trivial, right? So as a phi manifold, as a phi manifold S1 cross X connected some S2 cross S2 to non-trivial S1 bundle over X connected some S2 cross 2, since they are still homeomorphic. So you can have a cobordism.
Yeah, but
yes, but it wouldn't be a. You might have that fiber bundle that Jianfeng constructed might not be trivial as a fiber bundle, but it could just so happen to be diffeomorphic to the standard manifold.
Oh, I see.
There's simpler versions of that. I mean, if you take non-diffeomorphic four manifolds and cross them with S1, they become diffeomorphic five manifolds, but not as bundles.
Oh, I see. Okay.
Yeah, so we treat this as four manifold bundles, not just five manifolds.
Okay. Thank you.
Okay. All right, let's continue. So, okay, so we have this, recall that this pin 2 is a one-dimensional Lie group sitting inside these quaternions. And for our purpose, we are interested in three specific representations. The first one is just the one-dimensional trivial representation. We denote it by R. The second representation is the one-dimensional representation with trivial action of S1. So namely, this component acts trivially, but this J acts as -1. So that's the one-dimensional representation, non-trivial representation. And the third representation we are interested in is the four-dimensional representation. So we know pin 2 sits inside H. So you can just act pin 2 on H by the left multiplication. So that gives us a four-dimensional representation. And well, I need to say there are a lot of other irreducible representation of this Lie group pin 2, but in the Stabilization situation, only these three representation appears. Okay, and the pin 2 equivariant Bauer-Furuta invariant, I will briefly talk about the definition later, but let me just say it's it's a element in the pin 2 equivariant stable homotopy group of spheres. So here I'm using this notation. Let V be a representation space of pin 2, then we can do a one-point compactification, namely adding a point infinity to form a sphere. So this will be a sphere, right? This will be a sphere with a pin 2 action, and we choose the base point to be the infinity point. So namely, so if you look at this, this is a 9-dimensional sphere. And this is a 7-dimensional sphere. Both of them admit pin 2 actions. And we are, so this Bauer-Furuta invariant is a pin 2 equivariant stable map between these two spheres. And we can also talk about Bauer-Furuta invariant, pin 2 equivariant Bauer-Furuta invariant of the unstabilized mapping torus. It's okay, so you can see that this number changed from 7 to 6. That's because now we don't have this summand S2 cross S2 here. And so so this is the Bauer-Furuta invariant for family, but one can also just talk about it for a single four manifold. And important example is the Bauer-Furuta invariant of S2 cross S2. So it sits inside this stable homotopy group of spheres. And and essentially because this NST come from this M by doing a single stabilization, we have this formula, the Bauer-Furuta invariant of the stabilized mapping torus equals the product of these two Bauer-Furuta invariants. So you know, if you have two maps in two elements in a stable homotopy group of spheres, you can just multiply them together. Okay. Any questions? Okay, let's move on. And okay, so from here we see that, okay, so from this formula, we see that it's important to study this Bauer-Furuta invariant of this S2 cross S2. And let's do that. And okay, so recall that we have this one-dimensional representation sphere formed by adding an infinity point onto R tilde. So this is a one-dimensional sphere with a non-trivial J action. So this is the picture. This should really be J. So we have this one-dimensional sphere, and this J act non-trivially. Namely, it's just by reflecting. It maps the blue part to the red part and red part to the blue part. And now we can consider a specific map from S0 to S tilde, namely the inclusion map of these two, of this 0 and infinity, these two black dots, into this one-dimensional sphere. So let's, we call this map the Euler class. Okay, so this is a specific map, and it turns out that the pin 2 equivariant Bauer-Furuta invariant of S2 cross S2 is given by this inclusion map. And now here is the key observation. As a equivariant map, as a pin 2 equivariant map, this map is not now homotopic, because, well, okay, so you may try to move these black dots along any part to the bottom, so to make it now homotopic, to make it into a constant map, but because of this non-trivial J action, you are not allowed to do that. Recall that the J action on S0 is trivial, so you cannot really move this point down. Okay, so this is a non-trivial pin 2 equivariant map. And because of this fact, this product could be non-zero. right? Because if this map was 0, then you multiply 0 with anything else, that you just get 0. But since this is non-zero, it's possible that this product is actually non-zero. And actually, we will, in our proof, we actually show that this product is non-zero. Therefore, we are able to distinguish it with the standard product bundle. And also, let me make a remark that if you forget about this J action, then this map, this inclusion map, is not homotopic. And that's essentially the reason why just using the S1 equivariant or the non-equivariant version of Bauer-Furuta invariant is not enough to prove the theorem. Okay, any questions? No? Okay, so let's move on to the next part. Okay, so it's in this part, I will briefly give the define Bauer-Furuta invariant as an element in the stable homotopy, equivariant stable homotopy group of spheres. And there you can see this interesting notation, big star. Here, okay, so here, recall that in the non-equivariant world, we use this little star to denote the grading, right? And the grading is given by Z. But in the equivariant world, we don't just have those trivial spheres. We have these representation spheres with non-trivial pin2 action. And we indicate that by using this big star to indicate that this is actually a ROG graded homotopy theory. So this grading actually is this theory is graded by the real representation ring of pin2. Okay, so let me give a very quick review of Bauer-Furuta invariant, how it is constructed. Okay, so we start with a general diffeomorphism on a spin 4 manifold X. Well, forgive me for abuse of notation. Now X is just a some spin 4 manifold. We assume pi X is simply connected, and F is a diffeomorphism. Then we also assume that F is identity on the homology, on the second homology. Then just like before, we can form a mapping torus. So this is a 5-dimensional manifold, and we treat it as a 4-dimensional bundle over S1. Namely, we have this bundle structure. So the base is S1 and the fiber is X. Now, okay, so we can look at the frame bundle of the virtual tangent of the vertical tangent bundle. You know, the tangent bundle in the fiber direction, and the frame bundle is an SO4 bundle over N. A spin structure over this family is just a spin 4 bundle P that lifts this frame bundle. Or you can just think it as a fiber-wise spin structure and patched together. And okay, so it turns out that when by this simply connected assumption, and because the base is S1, there are always 2 spin structures. And let's just pick any one of them. Then we have the Selbert-Witten equation that will give us a map SW from H0 to H1. Here, H0 is a Hilbert bundle over S1, and H1 is a Hilbert space. Okay, and this Selbert-Witten map can be decomposed into 2 parts. The linear part, which is a fiber-wise Fredholm operator, and the nonlinear part, which is some zeroth order quaternion, quadratic. I guess I'm sorry, I'm switching the notation. It should really be H0 and H1. Anyway, so we have here H plus here means H0 here. It's a Hilbert bundle, and H minus here is H1 here. It's a Hilbert space. Okay, now we pick finite dimensional subspace W minus of H minus, which is transverse to L. and we let W plus to be the inverse image of W minus under this linear part. So it will be a finite dimensional sub-bundle of this Hilbert bundle. And after modifying this nonlinear part, one can get a approximated Stabilization map denoted by SW. It goes from this finite dimensional vector bundle over S1 to this finite dimensional vector space. And because the Stabilization equation has pretty nice compactness property, this little SW is actually a proper map. So we can form a map between the one-point compactifications, namely we just add infinity point on both the domain and the codomain. So we call this compactified map by SW infinity. So the domain now is the Thom space of this finite dimensional vector bundle over S1, and the target is just a sphere. And moreover, because pin two Stabilization equations over spin 4 manifold has a pin 2 symmetry. That's essentially the reason why we care about pin 2 equivariant theory in this setting. So because of this approximated Stabilization map has a pin 2 is equivariant under a pin 2 action. And moreover, both the domain and the target, this vector bundle has a canonical trivialization. It's just S1, it's a trivial bundle, S1 times this representation space. Okay, so, and W minus also has a canonical trivial identification with this specific representation space. I was being a little vague about this construction. There are some subtle construction needed in this choice of finite dimensional subspaces to make this work, but I won't go into that detail. So anyway, so there is a canonical way to identify this, both the domain and the target with some specific representation space. Okay. And by doing so, we can treat this compactified approximated Stabilization map as a map between this specific pin 2 space with and this specific pin 2 representation sphere. So here, this wedge means smash product. And here, I'm doing this S1 disjoint union with a distinct base point. Okay, so this is a map, pin 2 equivariant map between these two spaces. And any questions? No? Okay, good. All right, and to go from this pin 2 equivariant map to the stable homotopy group of spheres, we need to do some simple equivariant stable homotopy theory. So here, to simplify the notation, let me just use G to denote pin 2. And let AB be two based finite GCW complexes. That's a generalization of CW complex to the equivariant setting. And we use this angle bracket to denote the set of based G equivariant map from A to B, and we quotient out by equivariant homotopy. So that's the unstable homotopy classes between A and B. And we also define a stable homotopy class by picking M and K to be very large number and set AB and set this stable homotopy class from A to B as this limit, as this unstable homotopy class from A smash, this very large sphere, to this B smash, this very large sphere. And this is essentially the stable homotopy group using incomplete universe. So where we just smash with these three specific type of representation spheres, not every representation sphere. So that's something called incomplete universe. Well, in our situation, this is enough. So that's how we define the stable homotopy groups. It turns out to be a group, abelian group. So, and we can also define this S1 equivariant stable homotopy group between A and B, or non-equivariant stable homotopy group between A and B in a similar way. And there is a simple restriction map that goes from this pin2's equivariant stable homotopy group to S1 equivariant stable homotopy group or non-equivariant stable homotopy group. Namely, you just forget part of the group action. Okay, so we denote this operation by RES. RES means restricting the group action. There is actually another way that goes from a smaller group to a larger group. That's called transfer map. But let me not talk about that. It's the transfer map is used in the proof, but it's let me just ignore that part here. Okay, and recall that from the construction of Stabilization theory, we have this pin2 equivariant map, right? So this is a pin2 equivariant map from this space, smash some sphere to this another sphere, and it provides an element in this pin2 equivariant stable homotopy groups. Okay, so because we are working in a stable world, you can just ignore this Mn. Okay, so that's an element in this stable homotopy group. Any questions at this point? Okay, yeah. So let's continue with this construction. And we have this element. It's still not an element in the stable homotopy group of spheres because this is not a sphere. It's a sphere with a destroying base point. In order to make it a sphere, we consider the embedding of S1 into this two-dimensional sphere as an equator. Okay? This is embedding, and we know whenever we have such embedding of manifolds, there is the so-called Pontryagin-Thom collapsing map that collapse everything outside a normal neighborhood of this embedding into a single point. So that provides us with a map from S2R to this Thom space of the normal bundle, and the normal bundle is trivial, so it's just this smash product of this one point destroying union S1 with this sphere, and this is the Pontryagin-Thom collapsing map, and it gives an element in this stable homotopy groups. We denote this element by P. And now if you compare these two, you notice that if you just ignore these representation spheres, the target of this P is the same as the domain of this map. So we can do the composition and get a map between two spheres. So that's the so-called pin2 equivariant Bauer-Furuta map, Furuta invariant. So it's an element in this specific homotopy group of spheres. And well, we define the S1 equivariant version and the non-equivariant version simply by restricting the group actions. And similarly, we can define the Bauer-Furuta invariant for a single four manifold. Then it's just an element in this homotopy group of spheres. And if you compare this with this, you see that we don't have this R copy. That's because this R comes from the base. Okay, so you remember that we are working with a bundle over S1. So this S1 provides this extra copy of R. But if you just work with a single four manifold, then you don't have this R. Okay, and any questions? Sorry for this long definition of Bauer-Furuta invariant. I just want to sketch this construction. How do you go from the gauge theory to this element in a stable homotopy group of spheres? I think this is really beautiful work of Bauer and Furuta, so I just want to give it here. Okay, so let's move on to the next part. So well, so for now, you just forget everything. You just know from the analysis, okay, we have an element in a stable homotopy group of spheres. Okay, and let me give the stabilization lemma, which is essentially a generalization of Stephen Bauer's connected sum formula. It states that, okay, so recall that we have this Euler class given by this inclusion. And this stabilization lemma states that suppose we have a family obtained from another family by fiber-wise stabilization, namely fiber-wise connected sum with S2 plus S2. Then the Bauer-Furuta is invariant. It's just multiplying this with this Bauer-Furuta invariant of S2 plus S2, namely this Euler class. So that's the stabilization lemma. Okay, now let's take a closer look at the proof of the main theorem. Let me recall a statement. The statement is that the once punctured Dehn twist from this X connected sum S2 plus S2 is not smoothly isotopy to identity. Recall that X here means the connected sum of K3 with K3. So here's the sketch of proof. As I said, we form the mapping torus of delta and delta ST. Delta is the Dehn twist. So, and they are both smooth bundles over S1. And we consider the Bauer-Furuta invariant. They are by the stabilization lemma, they are related to each other by multiplying this with this Euler class, ER tilde. And then let's, okay, well, suppose this delta ST is smoothly isotopy to the identity, then this would be just the product bundle. So it's just, this will be the product bundle. And we know if you use the product spin structure on product bundle, the Bauer-Furuta invariant will always be vanishing. Therefore, it's enough to show that this Bauer-Furuta invariant is non-vanishing for both spin structures on N. Recall that N has two spin structures, and we need to show that both spin structures satisfy this inequality. And how do we show that? Well, let's denote this element, this Bauer-Furuta invariant by alpha. Okay, then we need to show that ER tilde times alpha is non-zero. Recall that the S1 equivariant Bauer-Furuta invariant comes from restricting the pin2 action to S1 action. So it's an element in this stable homotopy group of spheres. And it turns out that this group is not too hard to compute. And it's actually, there is a split exact sequence coming from ZIMO2 to this group and maps to T. There is a surjective map from this group to T. Okay. And actually this map is familiar for us, because if you apply this map on the S1 Bauer-Furuta invariant, you get an integer. That's just the family Selbert-Witter invariant of the family of N. So this is how one obtains the Selbert-Witter invariant from the S1 Bauer-Furuta invariant. It's essentially this map. And the kernel encodes some torsion information in the higher dimensional moduli space. Okay. And here is the lemma. The family Selbert-Witter invariant of this N is vanishing. Well, that's essentially because N actually can be formed by fiber-wise connected sum of two K3 bundles. And there is this vanishing theorem for Selbert-Witter invariant of connected sum, right? So that can be generalized to family version. And from there, we see that this restriction, this S1 Bauer-Furuta invariant actually belongs to this kernel. Okay, and now, okay, so we prove by contradiction. And suppose this ER tilde times this alpha equals 0. By some, well, not too hard computation in equivariant stable homotopy theory, one can conclude that any beta in this group that satisfy both this condition and this condition, namely, suppose it is annihilated by this Euler class and it has vanishing Selbert-Witter invariant, then we conclude that the restriction of this beta to the S1 group will just be 0. And if we apply this lemma to this pin2 equivariant Bauer-Furuta invariant, we see that S1 equivariant Bauer-Furuta invariant of this family N is just vanishing, it's just trivial. And in particular, that implies the non-equivariant Bauer-Furuta invariant of this bundle is also trivial. However, this is a contradiction because Peter and Tom, they actually show that this non-equivariant version of Bauer-Furuta invariant equals eta cubed. So eta is the Hopf map. So it's an element in the first stable homotopy group of spheres. And eta cubed is a non-trivial element in pi 3. They actually prove their theorem that delta itself is not smoothly isotopy to the identity by showing this non-equivariant Bauer-Furuta invariant is non-zero. And by this argument here, we get a contradiction. So this finishes the proof. So you can see that it's, the proof of the main theorem is based on Peter and Tom's result and some calculations in equivariant stable homotopy series. This is not very hard computation, but I think it's, well, I think this is a good, it's a good way to advertise that equivariant stable homotopy theory can be useful in studying low-dimensional topology. Okay, I think that's all I want to talk today, and thanks for your time and attention, and stay well and healthy.
On Zoom, it's possible to click a clap button. Are there further questions?
I have a question.
Okay, yeah.
So it just in principle, Jianfeng, could you use a similar method? Sorry, Jianfeng, could you use a similar method to get a counterexample to the one is enough for like a single manifold?
That's a great question. I thought about it, and it turns out that if my calculation is right, one needs some non-trivial Bauer-Furuta invariant not coming from connected sum. So you know, Bauer-Furuta invariant is for a single manifold is interesting. It's interesting only when the expected dimension of the moduli space is greater than 1. Otherwise, it's just a Selbert-Witten invariant.
Right.
And suppose one can get some interesting example of Bauer-Furuta invariant, of higher dimensional Bauer-Furuta invariant, that doesn't come from just taking connected sum, then yes, then there is a possibility that one can get such counterexample of one stabilization is enough for diffeomorphism problem. And but yeah.
Just it's a funny thing. I mean, I guess you had said at the beginning there was this older work of Fitzgerald and Stern, where they also had something that in principle was sensitive to connected sum with S2 cross S2 or could detect that. But that also just for sort of, I don't know, dimension counting reasons just never seemed to work.
I see. Well, maybe there is, well, my guess is that there may be a higher dimensional generalization of that invariant, making use higher dimensional anti-self-dual moduli space and pin tools and spin structure. And that could detect something interesting, but I guess the calculation is extremely hard also.
That's a follow-up.
Sure.
Yeah, I guess maybe actually it's not so much a follow-up as like boiling down, but is it fair to say that part of like the underlying moral of what works here is that, you know, even if some four manifold has trivial invariants, the diffeomorphism, the invariants associated to a diffeomorphism of it don't need to be trivial?
Yes, I think that's the right philosophy. Yes, so you can, the diffeomorphism, if you want to use gauge theory to study diffeomorphism, you want to study like family version of the invariant. And even if the gauge, even if the fiber-wise gauge theoretic invariant is trivial, the family version may be non-trivial and tell you something interesting. Yeah.
Okay, so I guess that's part of why it's not simple to go from obstructing diffeomorphisms from being isotopic to actually just showing that some smooth structure is exotic, because you have the extra layer of detection or whatever.
Oh, sorry. Could you?
Well, I was just saying, I guess, like, if the principle is relying on the fact that diffeomorphisms of you know, manifolds with trivial invariant can be non-trivial.
Yeah.
That doesn't necessarily get you to situations where you'd want to actually distinguish the invariance of the underlying four manifold if you're just trying to compare two different four manifolds, as opposed to study some diffeomorphism of a four manifold. But the second part, I'm just like processing your answer to the first original question.
Okay.
So I wouldn't worry.
Yeah.
Thank you.
Okay, thanks.
Okay. So I will leave this open for, another 10 minutes or so in case people want to ask Zhenfang questions as people go away. Let me announce that the next talk will be Wednesday, April 8th at 9 a.m. Pacific and at noon Eastern time. It'll be John Baldwin speaking virtually for us. All details will be on this Gauge Theory virtual website. I've made a recording of this presentation, and the recording will be posted on the website just as soon as the video processing. So, probably a couple hours if you want to watch it, and I'll move this to a past talk section on the website. I also welcome, maybe not in the group forum, but if you want to send me email suggestions to make things go smoother if there are problems with the moderation or video or the website.
Can I ask another question?
Sure, yeah.
Can you say anything if you just connected some with CP2?
Connected some with CP2, yes. If we connected some with Dehn twist with CP2, then the result, then it's mostly isotopic to identity. Actually, this kind of boundary Dehn twist is mostly isotopy to identity whenever you have a non-spin manifold. So yeah, so this is actually, I think my feeling is that in this kind of problem, spin world and non-spin world is really different. So if you just do untwisted stabilization and stay inside the world of spin manifold, then you may still get non-trivial elements. But as long as you go outside the spin world, the diffeomorphism becomes identity.
Okay.
So why is it isotopic to the identity in the non-spin case?
I think it's okay. I think it's because you can use so in a non-spin case you can find a sphere with odd self-intersection number, and then you can just do some local untwisting stuff.
Question, do you know if, or do you have any thoughts if 2 stabilizations is sufficient?
That's a great question. I don't know. I guess that's a really natural question. And we know the minimal number of stabilization needed is somewhere between 2 and I don't know, some finite number. And I guess it's a really natural question trying to think about that. But I don't know. I don't really know how to do that. And it'll be interesting to see what's the actual answer.
John Baldwin is being buried in children there.
Hey, John. Hey, Tom.
Hey, Zhenfang.
Hey,
how you doing out there?
Well, I'm doing fine. Just teaching. Yeah.
As well as the rest of us, I suppose.
Yeah, I have never done online teaching before, so it's new to me.
Yeah, we're all learning fast. You did a great job with the talk. It was very clear.
Thanks.
Now, one thing I think would be a nice tradition of when we do these things is, usually many of us mute our cameras. It'd be nice if before we all sign off, we unmuted our cameras and sort of just wave to each other or something to, it's nice to see everybody.
Yeah, it's nice to see everybody.
I think Selman had another question.
Great to see so many people. Oh, Matt. Okay, great.
Okay, good. Okay. What's the question?
Oh, yes, me. So there are examples of four manifolds. And when you do Glock construction, you get a diffeomorphism to itself. So can you work with those examples? You know, the diffeomorphism you obtain after the Glock construction compared to identity to show that
Okay.
they are not isotopic.
Good question. Well, I haven't thought about this, but my intuition is probably no. Because, well, I'm not 100% sure, but intuition is probably no. The reason is that, okay, so when you do Glock twist, okay, so the twist I'm doing here, or this twist considered by Peter and Tom, the interesting thing about it is that both pieces are complicated enough. So they're just K3 surface. But if you do Glock twist, one of the piece is simple, and that doesn't mean the twist is trivial, but I think it implies that gauge theory is not strong enough to tell you interesting things.
But you can start with a complicated manifold, do a Glock construction, nevertheless you get a diffeomorphic copy. Compare those two diffeomorphisms.
Yeah, but the diffeomorphism will extend outside like the normal neighborhood of a sphere or something, right?
But sphere can be sitting in a complicated way. Even can have some homology, can be going through the homology classes. And we have
Can I make a comment?
Sure.
I think part of the problem is that the Gluck twist, it's like the Dehn twist is really, it's sort of like a symmetry of the smooth structure. The Gluck twist isn't itself smooth. It's just that before and after you happen to get diffeomorphic things in that case, right? It's not necessarily providing for you some interesting diffeomorphism of your manifolds. Does that make sense? That's my take, I mean.
Well, you have to know how you obtain those diffeomorphisms after Glock construction. It's not easy to describe like the Dehn twist, but there are examples like this. When you are true with your proof, you have a diffeomorphism in your hands, and then you can ask the same question: how trivial is that diffeomorphism? I mean, just a wild idea. I don't know. Because a lot of times, you know, when you work on Glock problem, there are very few of these, and it takes huge amount of work, and you get a diffeomorphism to standard manifold. So this work has to codify something about this diffeomorphism. Right? You go from manifold to itself, diffeomorphic copy of itself, how you went to a diffeomorphic copy. So this is a problem about diffeomorphism.
Yeah, I don't know. Yeah, I think it would be fantastic if gauge theory can say something about Glock twist. And well, I don't know how to do that.
Anyway, this is a very interesting talk. Let me
Thanks.
think about homotopy theory more. So,
well, I'm learning something from my collaborators. They are algebraic.
It's good that Tom and Peter brought our attention to this.
I'll follow Tom's request and wave and say hi, and then I'll turn it off. Okay. You don't need to see my ugly video, but.
Okay. Bye, everybody.
Yeah.
Stay safe.
Bye.
Bye. Thanks, Jinfeng.
Thanks for organizing this.
Yeah, thanks for organizing this. I think this is a fantastic seminar.
Yeah, thank you.
Okay, I guess I also have to go.
Hey, Kyle.
Okay, thanks. Take care, everybody. See you next week.
Bye, Steven. Bye.
Yeah.
Oh,
John, look forward to your talk next week.
Personally.
Hey.
Bye, Boyu.
Hi.